All right. So welcome back to part 3. Today we're gonna basically take a look at everything that we went through so far and put it into context of actual useful stuff. So last time we spoke about the building, right, and how we can use for each loops and for loops to create variations of the same thing. So this is basically what's happening here as well. I am basically creating 5 different buildings because based on the parameters that I promoted here, building height, window size, width and depth of the building, and the seat, I'm basically always referencing the iteration attribute that we discussed earlier on the meta node. So basically, again, as a refresher, on that meta node, there is an iteration value, and that's basically unique for each loop, basically for each geometry. And based on this, you can see the building height increases and also the shape, etc. And the cool thing about this is basically, I can create 5 variations, but I can also create 10 variations of the same thing. And it basically spits out procedurally these buildings. And they're all living at the same spot, basically, which is what I want if I want to instance them. However, I can also stack them like this, because basically what's happening here is I'm just setting the position, X, Y, Z, right? So X is basically my point number times this channel, which basically just defines a multiplier for that distance, and then Y and Z are 0, because otherwise they would get copied in Y as well. So if I change this to 1, they would basically go upwards, or 10. Cool. So how can we put this into something useful before we jump into fluids? So we could potentially, for example, take the same exact setup, which is just creating random buildings, and copy that to points. So in this case, I'm just copying it to these points, and it's just a sphere that is then noised up, scattered a bunch of points, added like an attribute variant attribute to it. And if I copy this now, I get all of these buildings randomly instanced onto the geometry quite quickly. And the cool thing is that if I put this now into the context of Solaris, so basically the USD viewer, and switch to Karma, which is basically the native renderer inside of Houdini, this is quite quick, especially if we take a look how interactive this is, right? It basically is a ton of geometry, but still we can basically look at it. I don't know why this is always jumping back. Yeah, and you can see it's like a lot of houses here actually, and we can even do stuff like instance this on top of another instance of the same thing. So it gets very, I don't know, Dr. Strangey. And in fact, if we don't even have to necessarily render this, but we can even do like a flipbook. And since it's so quick, stuff like doing a play blast of an actual path traced renderer for preview purposes becomes basically very straightforward. So as you can see this here, this is basically, I think it takes literally 1 second per frame. And, just to mock up an idea, this becomes pretty powerful. And This is not only true for, stuff like procedural buildings, but also for stuff like simulations, for example. So if I switch this off and we go, it's basically like a preview of what we're going to discuss today. But if I do the same for the fluid, you can see how quick it basically resolves the image. And in fact, this is actually also simming live. So you can see the blue bar here in the back, which is basically the stuff that is already cached of the fluid sim itself. But if I don't, if I just jump to a cache to a frame where it hasn't been simmed, it basically catches up in the background. And so this is not only rendered more or less in real time, but it's also simmed more or less in real time. So there is no cache whatsoever in this whole scene. Basically, just everything gets generated on the fly. And so this is basically what we're going to talk about next. But before we do, I just want to show something that we did discuss last time, which is basically we can take this, right, and put it into an HDA. So what I did is I created a quick little HDA that basically, lets me create this abstract city. And it's exactly the same as we discussed before, the building in a for each loop. And then it's copied onto this noised up sphere. And this is then gets basically generated here. And I created an HDA out of this by just selecting it and going to assets, new digital assets from selection. And that basically lets me, save that as an HDA. And that HDA, I can then go in, and this is Unreal. Looks familiar, so I can put the same thing into Unreal pretty easily. And it basically generates the geometry on the fly as well there. Because again, what's happening in the background is that there is a plugin called Houdini Engine here at the top. So it loads the tool and an instance of Houdini that generates the geometry. And the cool thing again is I have two HDAs, one for the city, this guy, and one for a single building. So what I can do is I can actually go down and in the parameters of that object, there's the same stuff. Probably it's a bit small here in screen, but there's the building height. So if I change this to 5, then it automatically updates also in Unreal. So basically all the parameters that I can change in Houdini, I can also change here, which is super powerful. And again, this thing, the city sample of Unreal, which is quite a famous example for building procedural cities, heavily made use of Houdini to procedurally generate New York City, basically, and have it live in Unreal. Cool. So with that out of the way, we can finally talk about fluids and basically the first setup. And again, this is a preview of it. And as you can see, it's not the greatest render of the world, but if we look at how long did this actually render, we can see it starts at frame 6. I hope that's not too small. And then, it started at 1853 and it basically rendered 50 frames. So from 6 to 56 in just a minute. So that's, a second and a half per frame or something. And this is basically, path traced render with a transmissive shader and depth of field baked in as well. So normally it would take a lot longer, and it's also live simming, right? Because this wasn't cached. So everything down from the creation of the source to to the actual simulation, to the actual rendering, is all happening live in under a second per frame, or in under 2 seconds a frame. And that's why I'm always like stressing kind of like the best DCC, because in a way you can really do anything with it, from procedural modeling, simulation, shading, lighting, rendering, anything in one DCC, and that makes it so much more powerful than, for example, our current pipeline, which a lot of departments are involved in shifting things around, and it's very, very kind of slow and very not interactive. All right, so cool. Let's talk about this. So it all starts with an FBX that I'm importing. And this FBX, if I dive inside, so basically what I did is I go to File and then Import, and then there's like this Filmbox FBX kind of thingy. And here I can basically just import an FBX file. Let me see if I can find this data. Yeah, breakdown freezes. This is just an animation that I downloaded from Mixamo of this breakdancing guy. You can actually look at it, I think, in here. So this is the geometry that I loaded in as an input. And again, since it's all procedural, I can download a completely different animation and use it in the same setup, and it would still update, render everything live just with that updated input animation. And the problem that we are facing is, I spoke about this the last time, I think, that if we look at this from the side, we can see this is 10 times too big, right? So Houdini is in meters, so we can see this guy is, 125 meters high. So it's 10 times too big. So what we're going to do is we're going to create a new geometry context. Basically, this is where we are prepping our source. And we are just object merging our animation from that path, basically, from the breakdown freezes, blah, 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 beta surface deform. So if I jump to this, that's this node, which I'm referencing. Good. So first thing I'm doing is I'm giving it normals, just in case it doesn't have already some. Then I am time shifting it and make sure I only have integer frames and set the start frame to 1. So that basically it doesn't error out when I go -1 in case I want to have pre-roll or something like this. Then I scale it down 10 times. So now it basically looks as if it's the right scale. He's about 1.80 meters or something, so human scale. And the trail actually computes the velocity, because if we look at our velocity visualizer here, like this, we can see that in the beginning it doesn't have any velocities, right? Even though he moves, we only have a p attribute on the points, but there's no velocity whatsoever. So a trail which is set to compute velocity will basically create velocities based on the subsequent frame, either before or the frame after. So this is basically the velocity approximation is basically set to backward difference, which basically means it will look, where was my point before? Where is my point now? And now that distance is my velocity. I can also set this to forward difference. So now my velocities look different, because now it basically looks, where will my point position be in the next frame? And then it basically calculates this based on that. The thing is that if I set this to forward difference on the first frame, it will have velocities. However, on the very last frame, it won't have velocities, right? Because there is no forward different frame to the last frame, but there is a forward different frame to the first frame, because frame 2 is the next frame. But if I set this to backward difference, then my first frame doesn't have velocities. So I can also set this to central difference, but so it basically just calculates what's before and what's after, and then it, based on this, calculates the velocity. But in my case, it's good enough if I just set this to backward difference and be done with it. A better approximation would be if I set this to central difference, make sure I do have subframes by just adding like another time blend. And setting this to central difference, and then say compute acceleration. This would basically create a new attribute called acceleration, as you can see here. And this is basically much better because it kind of interpolates between two frames, and based on a bicubic curve. So this is good for curved motion blur, because so if you have, I don't know, like a helicopter and you have like spinning the blades, then you might want to have acceleration motion blur. However, it's a bit more expensive because on render time you have to tweak it a little bit differently. But again, for my purposes here, I think it's good enough if we just compute velocity. Cool. Then, since I don't have any UVs yet, if we go to vertices, actually I do have UVs because I created, no, it actually comes with UVs. So all good. My model, my initial model comes with UVs. I think I can preview them somehow. Yes. So these are my UVs, but the problem is that my UVs, of course, live on the vertex level, and I want to have that on points level. And the reason for what I want is that on point level is that basically my output of my fluid sim will be a surface that is based on points. So I'm not outputting vertices. So again, that's a cool thing. We can easily say my UV attribute, I want to change the class from vertex to point. So now my UVs are not present on the vertices anymore, but we have them on the UVs, like so. So this is my geo out, and we do this quite a lot. We just create a null and call it, in capital letters, geo underscore out or out underscore geo. And the reason for that is that if we want to object merge anything, so basically reference a geometry into another context, for example, then it's much easier to find this if it's capitals and it starts with out. Because in the hierarchy, basically everything that is capital gets displayed the first, and out is basically the first thing that it's basically referencing always. So if you ever wonder like why in any tutorial you see these nulls without something, that's basically the reason. Cool. So we have our dancing guy. He has UVs on the points, and he also has velocities. They are straight and not curved, but for our purposes, that's good enough for now. So what we do now is we create a surface, and there is an HDA for that. If we go inside of that HDA, it's basically converting this to a volume and points as well. So if I click on this, this geometry gets basically quite low res and voxelized. We can see actually the individual voxels. And if we hover over it, we can see that it now consists out of points, 3000 points, and a volume called surface. And this is what I also basically teased last time, that in flip sims, in fluid sims, it's still a particle simulation, but the particles are basically held together by a volume. So to create these nice, volume sheets, fluid sheets that we always want, or like tendril stuff. Otherwise, a pop sim would just the points would just go away in space, but this volume tries to narrow them together. in its volume space. So basically, the volume is telling whenever you go outside of my volume bounds, I'm pushing you back together a tiny bit, and that makes the particles output so stringy and nice. And so now basically we have again points and the surface. Actually, I can preview this, actually delete everything but keep the points. And now you can see that basically it's creating this surface, which is this volume, and these points. So it's still a particle sim, but incorporated inside of a volume. And this is the first thing that I'm creating. And I am transferring back my UVs. Because as you see, so on this geo, I still have my UVs, right? But if I create a surface out of it, it loses these UVs because of how this HDA basically works. So what I can do is I can transfer basically my UVs back to that new geometry from my initial points. So basically, like in the very beginning, when the red sphere transferred its color to the green sphere, the very basic example, this basically transfers now the UVs from this geometry to this geometry. So now basically we see in the contact sheet we have UVs again on point level. And the second thing that I'm generating is based on my velocities that I generated, I can generate another volume called velocity that is based on my point V attribute. So if I hover over this, you can see this has a velocity volume that basically is a vector volume. So it has X, Y, and Z. And it basically describes the velocity in each voxel. So that's a lot of we created a bunch of things and now it looks super weird because now we have this dancing blobby guy and there's this weird cloud around him. And this is basically just, Houdini is not really sure how it should display a velocity volume. So it basically says, there is info here, so I'm just going to show it as this weird cloud. So altogether, this equals to this surface, out surface, so to this guy, and this is what we're going to feed into the DOPNet. So if I go to my DOPNet, this is exactly it. So I have my flip fluid object, and I do have my flip solver. So it's always the same. It's always the same principle. You have a flip fluid object or pop object or RBD object. Then you have your solver. In this case, it's a flip solver, but could be a pop solver, could be an RBD solver, could be whatever. And then you have your source. In this case, it's a volume source. Same for pyro. It's also a volume source, but for pops, it's a pop source. And for RBD, it's a RBD source. So what I can do is, I'm putting my flip fluid object, which basically just defines my domain, my container. So where do I want to simulate my volume or my fluid? It basically describes the container outside of here. And if I maybe just disable all this kind of stuff for now, we see that, here I'm referencing my source that we just looked at, the wobbly guy of the cloud. And I'm just taking the velocity. So I'm just I'm importing this out surface, which has the surface volume, my velocity volumes, and all the points. And I just want to import the velocity field. So I can basically scale that separately and have that in the volume velocity tab of that node. On the sourcing itself, I'm referencing the exact same. So I'm still referencing out surface, but this time I'm not importing the velocity, but I'm only importing the surface, basically. So that's blobby volume that we looked at. And this then gets all fed into the flip solver. We add some gravity, we add a ground plane, so it collides with the ground plane. And there you have it. So now the thing is that we can see we're just looking at points again, right? But what's happening underneath is actually a lot more. So if I visualize, for example, my surface, it's still there, right? So it's not only advecting the points, but it's also advecting from my original blobby volume, advecting that volume, that surface volume, and it's using the velocities for it. So I can also display the velocities like so. And that basically, looks a bit funky, but you can see that based on my initial velocities that I just created from the movement of that animation, it basically takes them and solves it together with the rest of the particles and the volumes. And as we have learned, simulation is basically nothing else than vector math, creating a vector, a final vector, and then it's basically just offsetting a given point in space to that vector. And as you can see, this is pretty quick. So I can almost, play this in real time, and then when it computes, it takes a little bit per frame. But there is also a trick that I want to do, and that is I want to, since it's Houdini, I want to drive my viscosity attribute by h. So if I plug this wrangle here into particle velocity, which is basically the only input that I haven't connected anything to yet, and I say my viscosity attribute equals my h, then what I get when I import this and I look at my viscosity attribute, and maybe I look at it through, I don't know, an infrared kind of thing. So viscosity basically describes how thick fluid behaves, so how much it sticks together. Caramel, for example, or chocolate is very high, has a very high viscosity. And the lower my viscosity, the more splashy it gets, and the more the particle basically moves. And this is basically the equivalent of if you think of lava, for example. Lava is, when it gets erupted, it's super viscous, or super, like it still moves. But then over time, when it cools down, the magma, the rock is actually cooling. So then it basically changes its state again to a more solid state. And that's exactly what's happening here. So in the very beginning, you can see that my values of my viscosity, if I look at it, viscosity, sorry, typo. It's basically 0 in the very beginning. And then the older it gets, the older the particle gets, because that basically comes for free from the particle sim, right? In the beginning, it's 0. And then the older the particle gets, it basically counts how long is my particle alive, the more viscous it becomes. So the more slow. And this basically prevents from, if I wouldn't have high viscosity, then my fluid would just like grow bigger and bigger and bigger, and the bounds of my volume will be at some point pretty enormous. So it's also an optimization kind of process. It not only does it look better because it's basically different, it's mixing different physical attributes, but it's also making sure that it doesn't splash forever, right? Because it's basically slowing down the older it gets. Cool. So any questions so far about this? Yep. Again, if you go into the solver, yes, Alessandro.
Yes, sorry, I couldn't find my button. You start from a geometry, and you imported the geometry when you want to just create some fluids. I don't know, say out of nothing existing, so
Mhm.
from scratch. How would you approach that?
So basically, we always need a source, right? But we can generate that source, of course, on our own. So if, for example, I have a sphere again, and I would just mountain up that sphere and give it, I don't know, some animation to make it look more interesting, like this. I can plug this in directly to here, and that will basically do the same thing. It will scale it down because I'm transforming the guy down, so I'm just going to disable this one. But it will, give me this. So now it's not a blobby character anymore, but it's a blobby sphere. And then this, would update in the simulation. Of course, this now looks a bit uninteresting, and this is mainly because of the animation it has. So there's two ways we can make this, more interesting. Either we increase the amplitude, for example, to make it more, and maybe even the speed of the animation. So if I change the pulse duration to 2.5, the resulting velocities of this thing will be much higher, right? So what that means is that my resulting, let's not go that crazy, my resulting simulation will be quite splashy as well. That's not a good example. Let's actually make this, can also push that in a wrangle. So that trail, I'm just going to say my V attribute, I'm multiplying this by, say, 5. So now my velocities go from this size to this size, right? So if I now feed this into my simulation, then it will be quite splashy. So this is the first, and we are just using initial velocities, right? We're just changing the velocity of our source. But what we can also do is we can create our own volume, which basically means if I take this box and I create my own velocity volume with a curl noise inside, for example, and then it doesn't matter. Actually, I can show this maybe here on my other screen. Let me figure this out. So you can kind of see this, right? Probably not great, but maybe better than nothing. But this would be potentially a good example. So here, oh God, this is worse. I didn't prepare this, so bear with me. But
Sorry.
this basically just a sphere without any animation on it, right? And what I'm doing is based on a box, I'm creating my own little volume. And inside here, I'm creating a curl noise. So basically an ambient noise, that I'm then binding, that I'm exporting as my velocity. So to preview this, what I can do is I can apply like a volume trail. So this is basically now a volume field that lives in this space, right? And I can use this in my DOPNet to basically say to my object, this is a bit of a different setup. To my source, I want to advect my source by the velocity of this volume. And that would basically result in this. So here we don't have any initial velocities. We are basically generating a velocity, an ambient velocity field. And this is then used to drive, the velocity out of that source. And there is 1,000 ways to do this, right? I could use a curve force, a pop curve force instead. So I'm experimenting with this as well, which basically takes just curves, splines basically, and advects that based on those. And then there is, I can add like a pop wind that we saw on the previous, one of the previous examples for this weird magical effect that we did. So to just like create an ambient wind, which is kind of like an ambient velocity field that we're creating, but not really. So there's a lot of ways, but generally it's always velocities that you're either having initially to drive your fluid sim, or you create an ambient velocity field that then basically your fluid is reacting to.
So it's just a matter of being creative in the setup.
Exactly.
So if we think of, for example, a container with still water inside, then you might rotate the container and create with some gravity to create waves, for example, inside that container.
Yeah. Or you would, you would inject velocities basically on a pulse basis. So you would like add vectors from left to right that would basically then push the whole thing a little bit to the right, and then it bounces back because it's colliding with the container and stuff. So yeah, that's actually a good saying. That is, if your source is great, then you don't have to do much in your simulation, because if your source, so basically all the the blobby guy or the noised up sphere that we are having here, or whatever it is in Houdini, if you dial in your source correctly and you spend actually the most time in dialing in your source, the velocities, how it basically reacts, then this setup gets very, very easy. Like you don't have to do much, because this basically just takes, again, your input source, and then it basically advects it by these velocities that are all created on your source. So that's why I'm always saying, like, take enough time to make sure your sources are right, because then the simulation comes for free, basically. And then for just as an comparison, this would be the same source. So I'm referencing the same source, the geo out, without fluid volume. So this is basically now just the pop simulation, just a particle sim of the exact same thing. And you can see it's completely explodes, and it doesn't have to do anything with the volume. It kind of looks like a weird explosion. And this is mainly because, of course, it's a flip solver, so it has different parameters than the pop solver, but it's mainly also because of that volume that keeps the particles close together and makes them kind of stick together based on the surface tension, based on the velocity, based on the viscosity, etc. And all of those attributes can be also found here. So age particles basically means it records the age of the particles when they get born 0, and then it consecutively gets higher. Read particles means after a certain time, when they reach a certain age, they would get deleted. And ID attribute is basically to what we discussed also on a later point, on an earlier point where I can say I want to exactly delete, these points here on the top without changing the point count down the line. And you can go in here as well because, again, the flip solver is just an HDA. And if you dive inside, you can see all this, right? And there is a bunch of, microsolvers in here. There is project non-divergent simulations. There's a lot of stuff happening here that, all are wrapped up in this flip solver. And if you, really want to go down to the micro level and change stuff down there, you can do this either by creating different forces, because, there is a lot of stuff that you can add here as well. And the cool thing is, flip is also a particle sim. So we can also use a pop wind, right, in here and drive that into the volume velocity or the particle velocity. And if I increase this now to 100, then it probably will break completely, but just to show it. So now it basically, you can see the initial frame even is completely exploding because it now calculates the vector between my initial velocities that are quite high already that you saw previously of that noised up sphere. And then it adds into the mix this pop wind, which is this ambient wind, which has an extreme amplitude. And that's why the resulting vector of each point is just like way too much. So it completely loses its fluid shape. Cool. And I should also say that this is great for, fairly small scale, mid scale, sometimes large scale stuff. But if you, for example, want to create an ocean, then, this would obviously break because you can't have, thousands of kilometers or hundreds of kilometers that you see to the horizon, everything filled up with particles, right? This would just not work. So what we are doing instead, it's a bit, again, nothing prepared, but we would basically create a large ocean, which I'm just gonna use the shelf tool for now to just basically show you the rough setup for it. So what actually an ocean is inside of Houdini is it's a grid. It's a big grid, right? That basically is, if you look at the numbers, like 3,000 meters long, basically in both directions. So 6,000 meters is 6 kilometers grid. And you scatter a bunch of points on them, and then there's this thing called ocean spectrum. And this basically is basically just a function that specifies the resolution of the grid, the speed of the length, the amplitude, the speed of the waves, the amplitude of the waves. You can instance waves using points, and then so this basically spits out a lot of or one function basically, and that function you can then apply to your ocean, to your grid. So basically, it's just an animated displacement, and you can see it's moving over time, right? This is basically now the preset for an ocean, and this is just a proxy geo. So this looks, of course, not great. This looks like shit because it doesn't have any resolution to it. But what it does in the background, it's creating a displacement map that on render time is applied. So basically, we're just rendering a grid, but it looks like a beautiful ocean because on render time, the geometry of just that simple grid gets subdivided heavily and then displaced by that ocean spectrum. And then if we have, just thinking if I should show this or not. Yeah, why not? So creature breach. Oh god. So this is a tutorial that I didn't do this. This guy is much better than me. But he's one of the greatest Houdini artists, and I just highly can recommend doing one of his tutorials because they're extremely efficient and extremely simple for an amazing output. So if you look at this, right, then obviously the simulation of the white water and the water itself, with all the waves that are created and stuff. So everything up here, that is particles. That is basically what we, in a very small scale, this did so far. So you can see this is, all particles. But the ocean itself, so everything down here, this is basically just the grid that we looked at with the ocean spectra displacing that grid. And this is basically, if I would, render this would actually look quite similar to this, because it would apply an ocean shader, it would apply some crisps, some white water there as well, and it would, instantly render in under a second or like 2 seconds, super fast, because it's just a grid with displacement on it and an ocean shader. And this is actually the heavy part. So this is basically our source where everything is like colliding with, and everything is based on particles. So we have the simulation, right? This is where it creates all these waves and stuff. But then we can actually see this here probably as well. So this is the actual fluid sim. This one. So this is the particles that you see, right? And you can see actually it's not that many. It's fairly forgiving, right? It's like we can actually make out the particles. So it's actually quite quick in comparison as well. Then the white water is actually the most heavy simulation on this whole thing, which is basically based on the water sim. But all of the high detail wave stuff here at the bottom, this is actually just a plane with a grid on it. And then he's basically merging both of these things together. So you have your ocean displacement, you have your big particle simulation, and then you're basically making like a fall off at the edges almost and merging that together. And that results in the impression that everything that you did, is right at the ocean. But what happens in reality is there is a particle sim here, and the rest is just a plane, because you don't need to simulate the millions of points to render an ocean. You just need a plane with a displacement on it. I hope that kind of makes sense. Cool. So we discussed the source. Oh god, now it's crashing. No. Yeah, let me maybe restart this guy. Probably I'm just doing too many things on my GPU because I have Unreal open in the back. Maybe let's close that as well. And all the karma rendering stuff that you saw is always also happening on the CPU and the GPU. So probably that was just my graphics card complaining that it's slowly dying. Okay, let me open up the fluid end again. And you can see now it's basically opening up the scene. And the last time I had the scene open, I was at frame 79. So now it's basically calculating the flip sim to that frame. So basically 3 seconds of simulation, it basically does it right now. So you can see it's a fairly simple simulation, and but yeah, it's basically just to make clear the basics of a flip sim. And the cool thing is, once we went through this setup, all the other setups that we saw, being like sand or whatever, they're like 80% the same. So again, we have the source that we then loaded in the surface and the velocity, put it into a pop solver. We set our viscosity equals our h, and the output of this is basically this. So it's a bunch of points with a lot of attributes on it. And this now there's basically a Houdini preset. It compresses the fluid, so it basically tries to make it very lightweight and kind of pack it. And so if we want to, and this is what basically gets cached. So if you want to cache a fluid simulation, then it's highly recommended to make it as lightweight as possible. This is set to write 16-bit floats, which basically means it's not how precise it saves the point positions and stuff. It's not on 32-bit but 16-bit, so a lot less data. And in fact, this really makes a difference. So if you wouldn't compress this and you would just save all the data, a lot of this stuff we don't need, like var map and next ID and rest in this case we also don't need. We could also delete this, but then it's so quick anyways, I didn't really care that much to make it more efficient in this case and optimize it, because it's already almost real time. So long story short, I'm surfacing this whole thing. So I'm importing the particles, and then based on the point position and all the attributes, it creates a mesh out of it, right? It's basically what you also know from, I don't know, RealFlow or something back in the days. But this is still like a poly soup, which is also still a more efficient kind of way to deal with geometry. So I want to convert this really to polygons. So now it's basically polygons again. And if I would save this, then this cache would be quite more heavy than what I would save when I cache this one. Cool. So actually, I'm not doing much here. Just making a surface out of this, and then I'm promoting the viscosity from point to primitive, because this is how I'm going to use it later in the shader. And I'm also promoting back my UVs from point to vertex. So if you remember, the moment when we created the particles on the source, we had to promote the UVs from vertex to point, then sim it, and now we do the opposite. We put it from point to vertex, because now it's not points anymore, but it's again a surface. Obviously, it's a different surface, different polygons that are our input, because that was just like dancing guy, the breakdancing guy. Now it's like this whole simulation, but the principle is always the same. I want vertex or UVs basically on vertex level, because this is where they belong, basically. And then I can, do like post operations, like smoothing the UVs a tiny bit to make them a bit less freaky. So I'm basically just hitting down a smooth. You can also like smooth based on position. This would basically smooth the whole mesh a little bit more, but in this case, I'm smoothing the UVs. And then this part is optional. because this is what actually gets rendered. And this is the bubbles. So look at this. The output of this is basically a bunch of bubbles that live inside of this geometry, right? And what this is actually quite straightforward. I'm taking my points of my simulation, so as it comes out of the simulation, and I'm culling randomly based on IDs. So I know that, this has a unique attribute. Each of them has a unique ID. So if I again click on this ID attribute, you can see that, each of them has a unique ID, which now is displayed as a color, but actually it's an integer attribute. We can also look at this here. So each of them has like a unique ID. And based on this, I'm just making sure that I don't want as many particles, so I can, just define how many particles I want to delete. So I'm keeping basically a third of them. Then I'm blasting away all the velocities and surface fields and everything that is not a point because I really don't need it. Then I trail it to give them velocities. I mean, this is quite optional because they already have velocities, as you might see. So here they already have velocities. I'm training them just based on their ID. So it basically tracks every point individually and gives them velocities, just to have like a fresh set of velocities without any simulation artifacts, if there are any. And then I'm randomizing, so I'm giving it a p-scale attribute that basically just defines how big each point is. And then I'm, mapping that to a ramp. So basically I'm getting, in this case, a lot of small spheres, and then a few very big ones. So if I change this here, this ramp, then I also changed the distribution. And this is basically, the classic power curve, what you want most of the time, be it in a destruction or RBD sim. You always want just a few big pieces, and then the rest is like very, very small. So we have these points now, and we have our surface. Problem is that if I look at the surface and the points, some of them are sticking out, right? I have the points also outside of that. So there's two ways I can fix this. Either I'm making a volume out of the surface and say, if you're outside of my bounds, I'm going to push you in. Basically, what a fluid sim is doing, what we discussed, right? It keeps the particles together because it pushes them into the center of its volume. Or, which is in this case a bit more straightforward, is I'm taking the geometry, I'm peaking it, so I make sure it's a tiny bit smaller. So you can see, if we zoom in here, it's a tiny, if I make this more obvious, then you see that, I'm shrinking the whole volume here. Yeah. So I'm just making it a tiny bit smaller, right? Based on the normals. And then I'm grouping the output of these points, right? These copied points. I'm grouping everything that is in a bounding region of my bounding object. And my bounding object is basically the geometry itself, so the surface. And I'm grouping everything that is inside of this, right? So good example is this one. These points of the sphere are living inside of the surface and the rest outside. So now I gave them a group name called $OS. $OS means just take the name of the node. And since the node I called keep, the group is also called keep. So what I can do then is basically I just blast keep. So I delete keep. So now this basically results in everything getting deleted that is outside of the bounds. So I don't have free floating bubbles anymore. Then I give it normals because just to be, clean. Then I delete. Oh yeah, I delete additional points, because what often happens is that sometimes when I delete stuff, then this happens. There is like a single point that didn't get deleted, right? It's not always geometry, because if just one point of a sphere is inside of the surface and everything else gets deleted, I end up with a single point. And that single point is then rendered as a point. And because I gave my particles here a p-scale attribute, which is actually not that small, 0.5, it happens sometimes that you think you just render these spheres, but there is a point. And if the point has a big p-scale attribute, if this is set to 1 meter, you get like a 1 meter ball in the midst of your render, because this is interpreted, this little point that you barely can see is interpreted by the p-scale it has. So if the p-scale is pretty big, then you end up with a big ball inside of your render. So to basically get rid of this, I'm basically deleting every single points that I have in the simulation. As you can see here, this guy just got deleted. So, and this is basically my second output. So now I have the surface, this guy, with my wonky UVs, and I also have the particles that live inside of the surface again. Cool. So next is basically rendering this all. So for this, we're going to go into the stage context, which is basically the USD environment inside of Houdini called Solaris. And this will take a bit of time to go through. But the cool thing again is that once we look at, the next one, the sand guy, for example, it's exactly the same. It's not a fluid sim, but it's a grain sim, it's a vellum sim. But the whole stage is exactly the same, minus the shader and minus the input. So it's, again, the proceduralism of Houdini gets clear pretty quickly by then, I think. Cool. So if I look through my camera here, like so, you can see that, I created the camera on my own with a bunch of keyframes. Basically, if I look at this, oh man, I think my near and far clip planes are a bit crazy. Yes. If I look at this, then I can see that there is my camera, and it has a bunch of keyframes. And if I disable my fluid here for a sec, because it's still not cached, so it's basically running in the background live. I'm animating on that camera, position, rotation, and also the distance of the lens, the focus distance, basically. Because if, again, we look at the raw render, we can see the focus shifts. So right now, my focus distance is focusing on, of course, this guy. But every now and then, we kind of lose the focus a tiny bit, like here, where the focus actually sits behind him. So not only the foreground, but also the midground gets blurry. So yeah, this is not the perfect camera, but it's a bit more dynamic than just a regular camera. So what I'm doing is I am importing my fluid, and I'm doing this by SOP importing it. So right now we're in Solaris, which means we are in USD land. So from now on, everything that we do here is living in the scene graph. And that's basically, it's a bit like the hierarchy in the outliner in Maya, where you basically say every object that I have inside of USD has a name and has a hierarchy that it lives in. And everything that I want to import into this new Solaris context, I have to, import in one way or the other. And in this case, I'm importing it through a SOP import because this is the context that it previously lived in, right? So if we go here again, we can see that this lived here, and this is the geometry context, and that's the SOP because it's a surface operators context. And to get this into the USD context, we just do SOP import. And we do it for the render of the fluid, and we also do it for the bubbles. So basically, we import both fluid and the bubbles. You see the bubbles here, and they over time change as well as the fluid, and we just merge them together. Then I'm also merging in my camera because my camera at this point doesn't exist, right? I don't have a camera here that I can look through. Once I merge in the camera, then I can basically look through my camera. And this is basically, you can think of this almost like a pipeline, because here at this point, I have all my assets, right, that are coming from assets, but I don't have layout yet, so I don't have a camera that I can look through. However, when layout publishes their camera, I can merge in the camera, and suddenly I have not only my assets, but I also have my assets in context of the layout. And this is actually exactly how USD is also working, because everything that I'm doing here, I can do USD ROP and export basically a single USD that is then called fluid dense USD ROP.USD, and I could open this USD in Maya, in Gaffer, at some point, sure, in Unreal as well, because it's the universal scene description, right? Everything that we're doing, assets, camera, lighting, shaders, shader assignments, everything that is needed to get to a final render is saved into a single file. And that single file, basically, every department contributes to that single file. So if assets creates an asset, it's saved as a USD. Then this USD gets handed over to layout, and layout is basically loading that USD in and adding its camera as a layer, basically, and saves this as a new USD. And then this USD arrives in animation, and animation does their animation. Animation layer exports that as another USD, and that's what we are opening at some point. We are adding our effects layer and passing that to lighting, and lighting is then rendering that resulting USD. It's basically the replacement for bundles, which is great because once it arrives in lighting, they basically have one USD, one single file for everything, that then they can easily turn off layers as well, or change or override stuff. So again, to show this off, I'm going to just switch to Karma XPU, which is, again, Houdini's native USD renderer. And I can also look through the camera already. And you can see stuff like depth of field is already computed here. So I can see that my foreground gets blurry and my background is blurry, and I'm focusing on this guy. However, I don't have lights in my scene because I'm looking at this, and my distant and dome light are merged in here. So if I display this now, then I can see, okay, I have actually a distant light and a dome light, and they're completely blowing out my scene because I don't have any shaders applied. So for this, I'm creating a material library where I basically have my shaders, one for the fluid, one for the bubbles, one for the ground, and then an alternative one for the fluid. And then I'm assigning those materials in the next step to the geometry. And if I would write out this USD, it would, depending on how I save it, would it be extremely lightweight, because it doesn't necessarily store, the heavy geometry each frame, but basically you can think of it as almost like a text file where it says, my heavy geometry lives here, and then this camera data is added to this, and then these types of lights at these positions with these values on it are also referenced in. And then I'm creating these materials, which are also just text, basically. And then I'm assigning this to the geometry. So in the end, you end up with a very, very lightweight single USD file that basically recreates this whole graph, and everybody downstream can actually change it. In theory, lighting can change, the camera, for example. That's all possible in USD because it's just one single file. Cool. That was a little, X course in USD. But the cool thing is that if I look at this now, I can see that my ground is missing, right? So if I merge in my ground, then I can see, okay, cool. I can look at this from different angles, not only from the cameras. And as you can see, it's resolving pretty quickly. And if I change here the frame, it almost interactively changes that as well. And as a matter of fact, we can see we have our surface and we have our bubbles as well. And the reason why this is not as fast as it could be is, first, I didn't optimize this in any ways because there's a bunch of attributes that I don't need. But also there is like a heavy dispersion on the Swiss fluid. So if I change the dispersion here to 0, then it's even quicker, as you see. Because dispersion is a quite heavy shader process. So if I up this again and maybe increase the depth, then you can see that in some areas we are getting this rainbowy effect depending on the depth and stuff. And this is quite heavy to render. But yeah, this is basically it. So we can almost live change also the shader. So in this series assign material, we can go to our fluid surface, for example, and say, instead of this material extended surface fluid, I want to add this one. And this one is a bit abstract, as you can see, but it brings another point across, and that is all the attributes that I previously used inside of Houdini, for example, the viscosity. I can use these attributes still and change my materials inside of them. Normally, this can be done in any DCC, of course. So if we export that attribute, that viscosity attribute, that gets higher over time, right? It starts very low and then it gets higher because it's based on age. If we would export this to lighting, then Jörg or Julius could basically use that to drive the whatever attribute inside of here. But the cool thing is, again, in Houdini, we don't have to export it. We don't have to cache it. We don't have to do anything because it's already on the geometry that we are live simulating, right? If we get a note, like make it less viscous, then I can do this in Houdini on the fly. I can say, I make it less viscous on my sim, and then I can also tweak the shader at the same time and have something much more quicker because I don't need to necessarily catch anything to the next department. And this is where, at the end, it's a cost thing. So this is why more and more companies are actually switching to Houdini also for rendering, because you can do stuff just way more quick than exporting it from one DCC to the other. Because if you can imagine, if I export this fluid, which is not very high res, but has a bunch of points to lighting, this will take a while, right? And I completely kill this waiting time if I just do it on the fly, basically. Cool. So what did I do here? I basically, if I go to the material library, I assigned this material. And this material basically just loads in a value called viscosity. So basically that's the value that we previously defined, that everything slowing down the older it gets. And then I'm mapping this to a ramp. So I can change the ramp colors here. And this will also, update live in the viewport. So now basically the area where the viscosity is 0 gets smaller and smaller, and the black area basically gets more and more. So I can change this basically on the fly, and then this is piped into the base color as well as emission I'm not using right now, but I'm also adding normals based on this image, which is just some random base color of some rocks, basically, to just get across the point that I exported the UVs for a reason, that if ever there are UVs needed to map a texture on it, then we totally can. And again, if I look through the camera, and it comes with depth of field and everything. Also, motion blur is baked in, as you see. I can also change the lighting pretty quickly. So the dome light, if I modify this to 0.1 to be a bit darker, and therefore I make my distant light a bit brighter, I can change the direction of the distant light. And there's a couple of cool tools that I want to show as well. So for example, if you're matching a plate, so you have a layout, you have your CG geometry render basically, and you now basically want to match the shadows of the plate. We could use, we could use the vector math that we previously did as well to calculate the direction of the lights, for example. So Houdini has, for example, this tool where you can select some point of the origin and then select another point, and and if I now change my target point, it will take the distant light and make sure that this throws a shadow here, for example. And this is just one of the tools that make it quite easy to, if you have a plate and there is a tree and the tree throws a shadow on the ground, it's super simple to match the position of it. I think Katana has this now as well. Not sure if Gaffer has it, but it's super handy. And same goes for stuff like specular. So if I want to have a specular hit here, I can basically just click wherever I want to have like a specular hit from each light contribution, and it just makes it super easy to basically have a base lighting going. And again, if I want down the line change my material to, I don't know, apple juice, then boom, it's apple juice, and again it renders more or less on the fly. The computational time that you see in the very beginning when I change the frame is in a big part, as you can see here, the particle fluid surfacing. So what we are still doing after the sim is we're taking all those points and then we're creating a surface out of those points, right? And that is actually the biggest part in this whole equation. This is why it takes so long before it starts rendering. As you can see down here, the particle fluid and the smooth and stuff. So yeah, that's a overview for the fluid section of the guy. And if I want to render this, basically all I do is I create the Karma render settings where I say, do I want to render this in CPU or XPU? And do I want to enable depth of field? Do I want to render with motion blur? Do I want to set my samples, add AOVs, what have you? And then I basically send it to the farm or do it locally with a USD render ROP, where it basically takes the settings of the use of the Karma render settings already. So I only have to say which frames I want to render and basically say render to disk, and that's it. Yeah, any questions?
With the render ROP, is the sim cached also on disk?
Yeah, it doesn't have to be. So again, since everything I mean, at least here on my local machine, right? It has a beefy graphic card, so everything that I'm doing, I don't need to really cache. So I can render frame 1, and then it would sim frame 1, and then render frame 1, and then it would sim frame 2, and then it would render frame 2. So it would just go through the whole graph and just do it consequentially. However, if I would send this to the farm, then it's better if I cache at least the particle sim, because otherwise, if I send it to the farm, it gets basically allocated to, I don't know, 15 machines, right? And every machine 15 gets basically, it starts with frame 200 and renders until 240 or something, because it's distributed. So this machine would actually first have to sim everything up until frame 200, and then it can start rendering. And so it gets slower overall because all of those 15 machines first have to sim and then render. On my local machine, it doesn't really matter because it's a single proc thing anyways. But on the farm, that's the reason why we would basically probably actually not render the final surface down here, because that's quite expensive. But we would export cache just this fluid compressed file cache here, which is basically looking like all the boxes here. And then all the stuff that happens after just takes like 1 or 2 seconds a frame. But the problem is, once we give it, for example, to the DCC, we absolutely have to give you this, right? We have to export this to Gaffer, because Gaffer doesn't understand what the hell this fluid compress should be, or what is it basically. And that's the whole gist about using Houdini. You can be much more efficient because you don't every time imagine this would be a shot like we just saw before, a giant creature coming out of the ocean. If there is a single node, please remove this wave or like these couple of particles. We don't like them. They're too blobby. What we would do is we would go back here, basically delete these couple of points, right? Delete them based on ID, of course. And then we would go down here and have to cache everything again and again and again. And this is then, of course, super heavy, right? And this is mainly the reason why if the render department, lighting department would use Houdini, we can give them this packed cache that is very efficient and these couple of nodes, and then they can render it on the fly as well.
Beautiful.
Yes, but unfortunately we're using Gaffer. So we can't.
Yeah, but it looks like, some things we are not exporting to Gaffer anymore.
Yes, and that's the reason why we have been pushing for support directly to comp as well, because exactly of that reason, it's much more simple to import a light rig and then use that to render directly in Houdini, sometimes at least.
Cool, thanks.
Thank you. And I mean, we have half an hour left, so it's up to you. I can talk about the sand guy, this guy, or I can talk about the RBD guy, or I can talk about the Confeti Guy. Actually, I think the Confeti Guy is my favorite. I don't know why, but it looks just so funky. Or we could potentially also look at this guy. I mean, not exactly this guy, but so I think this was on another slide as well at some point. The plants that are growing. This was all rendered with Karma XPU. Actually, it's over, like that's from 2021 or something. And there it becomes even more crazy because the plate I shot just on my phone, but all the shadow matching to the plate was done as I showed you before with, you point the source and the target of the shadow and stuff. And using XPU, it's just the iteration times. That the more iteration you can do, the better the image looks in the end. And this, in the end, I mean, this doesn't look like production ready yet, but it took no time and it rendered in a second per frame, basically. And for me, that's just like super cool. And it's not even a simulation, right? This is basically just a for each loop with a time offsetted animation. So basically what this is it's a curve that basically starts here and, gets created, gets longer over time. And then based on the points of the curve, the older the point is, can imagine like this point is very old, the more I'm offsetting the animation of each leaf, which is just a leaf animation in the origin going up. So basically this one, because it's pretty old, is already opened, but this point just got created. So basically that animation gets time offsetted to that point. So at this point, it starts growing. And then it basically reaches its end of its animation, and then that's it. So this kind of looks like looks like a simulation, but it's actually not. It's just time offsetted for each caches, basically. So yeah, up to you. What would be more interesting? There's the pyro guy as well that I don't like too much. Sand, RBDs, and confetti, basically, or the plant grow setup, as you guys want. Okay, so we have one vote for Confeti Guy. Okay, then we leave it at one vote for the Confeti Guy. And again, the point of this is, if you've seen this, right, and I'm opening up now the Confeti Guy in another instance. Confetti Dance, I think it was called. You might notice that 80% of the node tree is exactly the same. So again, we start with our animation of the breakdancing dude, and we load that into Houdini. Actually, this is not moving. Let's see why. Probably something is broken. I'm just going to re-import it. Okay. So, and file import FBX data import. Good. So now we have our FBX back. It's kind of working. So now, since our object merge is relatively linked to the output of this breakdance guy, I just can re-import him, and this will look at the same path because the node is called the same. So I don't have to re-import him. It's just takes it automatically. Again, I'm giving him normals. I'm time shifting him to make sure that I only have integer frames, and I'm clamping him to the first. I'm scaling him down so that from my camera it kind of makes sense. I'm giving him velocities by trailing him. Like so. So this is exactly the same of what you've seen before, right? And now comes the change. So I'm time shifting him to, again, just having integer frames. This is a double, so I don't necessarily need this. I can also actually, let me check something if this actually is correct, because I think this should be, yeah, I think this should be actually the first frame. So let me put this to frame 1. Yeah, so this is just still the animation. And now this is the first frame. And oftentimes we use just the first frame or the T-pose of the character as well to do operations on him that are static. So for example, in this case, I'm quad remeshing him. I'm deleting a bunch of points. I'm checking the connectivity that you know from a previous class, where we basically give a class attribute to each connected primitive. We give it a different color, in this case a white color. We create UVs again, and then we fracture the guy. So can't really see this, but if we explode him, we can see that we fractured him with this edge fracture, which is very straightforward because it just, says how many pieces should I fracture him into. So there's not much control here. But the gag is that I'm doing this twice. On this guy, I'm doing 5 pieces, and here I'm doing 10 pieces. And then with a switch, I can basically specify which one I basically want to use. And I have the feeling that this is actually not the latest version, but let's keep going. So I have this fractured guy now, which basically more or less looks like this, right? But together, but you can't really see that it's separate pieces now. And then I'm basically point deforming this modified geometry back onto the animation. So now I do this. I'm basically retargeting, and point deform, I think, is one of the greatest nodes in Houdini because I'm just using it so often. Point deform basically says, on my first input, I want you to connect the mesh that you want to deform. On the second one is the rest point lattice. And on the third one is your animated geometry. So long story short, this is the heavily modified geometry, right? Where this is actually completely different topology because it, consists out of much more points because like edge fractures and what have you. However, I have the same geometry untouched here. Right? This is my untouched original geometry that is also static, right? So the only thing that this and this geometry have in common is that they roughly live in the same space, right? This guy is even missing fingers because of the quad remesh and stuff. So this is completely different geometry. The UVs are in a similar space, but all the rest is like completely different, point count, everything. But this is actually good enough for point deform because it can take this geometry and this geometry as long as they are both static and in the same place. And then based on the third input, which is basically your second input, so the static one, but animated. So this guy is moving and has all the same attributes, all the same objects, everything the same as this guy, which is completely frozen. So I can basically do whatever I want here. Can do something ridiculous. And I don't know, poly extrude this guy and make him a unicorn. Like this, and twist it because then it gets even more ridiculous. So now he's kind of like a unicorn, and the point deform will still work. Right. So I can give him a sword in the hand, and the sword will basically be point deformed to that original geometry. And so, yeah, it's basically just a lookup of with a radius, basically, and a sampling. So in this case, I'm sampling 100 points with a radius of 0.1, but this can be used in so many different scenarios. For example, on Grow, we had this shot where we got Quixel assets, Quixel trees that we should make grow inside of Houdini. So what we did is basically we created a skeleton, a representation of these trees, and that is just curves. And then we let those curves basically grow over time so that the trees get bigger over time. And then we basically use the pointiform to say, here is my initial tree, here is my initial curve that is the same position, and here is the heavily modified version that is actually growing, and it just worked. So there is an article from one Houdini artist that says pointiform anything, and I think it's very valid because you can pointiform anything. You can use an exploded view of this guy and retarget it back to the animation. It's as if you have a character and then you say, the animation of the character changed, or he now has a belt, basically. Can we please add this to the rig? And please update the rig and then update the character and then update the animation. Well, with pointiform, you just add the belt and it just works, and you don't have to update anything because it updates the animation live. Cool. So that was a commercial break for pointiform. Then I give it new velocities, because if you can imagine that, actually I'm not giving it new velocities. I'm trailing him a tiny bit. So the trail stop by default stands for on preserve original, and then you can basically define the trail length. So if I set this to 24, then it would basically just trail the whole geometry 24 frames. So it gets this very abstract thing, which sometimes is, however, pretty useful. And in this case, I'm just using a trail length of 2 to make it to have basically a little bit of an echo effect here on my source. And again, I'm using out surface. I didn't even rename the node. Technically, it's wrong because it's not a surface for fluid sim, but it's basically just an input geometry, but I didn't even care to rename it. And this now goes into, again, the sim. So you might notice that last time we looked at the DOP net directly. Here, I'm actually not doing this just to show that there's also different ways of doing it. So this is SOP land, right? Geometry land here. And my sim is still geometry land because I'm still doing stuff to the source. So I think actually the setup is a bit broken because this was the reference link was also not working, but let's see what we get. So again, I'm object merging what we just created into this new context. Then I'm saying nothing. Okay, probably that's somehow broken, but let's see what we get. I'm converting this into vellum constraints. And if we look at what vellum is doing, so vellum is fairly new. It's a couple of years old. It's basically, the idea is rather than doing complicated rigid body simulations, the idea is let's take every point there is on a given geometry and say let's just simulate on those points. So basically it's a PBD solver. It's a point position based solver that is, each point is just held together to a different point by a constraint. And it heavily depends on what type of constraint that is and how this constraint is connecting to the next point. So, for example, on this example, it created out of these points a fairly straightforward connection where every point is multiple times connected to the next point. And this is because I said it's a vellum cloth constraint. So it's kind of like a preset. And if you remember, though, the geometry that we're importing consists out of these broken pieces, actually, right? So it's not unified geometry, but it's actually a lot of broken pieces together. And therefore, I have this vellum stitch, which basically stitches the geometry together wherever they were fractured in the first place. And that's a bit complicated, but then I'm taking this as a source, and then this is not the right setup. Shit. It's some weird in-between version, I think, that doesn't really. Let's see what it spits out. Nothing. Yeah, that's what I feared. Collision geometry. Yeah, that's not the right one. Let me try to open another one. Cloth dance should be confetti dance. I'm very sorry. This I wasn't expecting to open this one, but let's open. Actually, let's try maybe RBD cloth. Yeah, let's open cloth dance because the setup is fairly similar. So this would be this one instead. But the idea is kind of like the same, where I'm fracturing the guy, and the only difference is actually the shader, because as you can see, the yellow value is driven by the velocity. So the higher my velocities are, the more yellow it is. But the rest is fairly the same. So let's switch to this view. So, okay, this looks again very different. Grains vellum. This looks suspiciously like the grain sim. Let's see. Yeah, this is actually the grain sim. Because here I'm creating, because for some reason all the hip names got mixed up. Because this is also right. Let me open up another one. Maybe this guy. Sorry, this should be a bit smoother. But I think since I did this a couple of times already for multiple schools, things might have changed a tiny bit. Yeah, this looks better. Okay, so it's the same setup, but this time it's actually the correct one. So again, if I look at this guy, this is heavily changed geometry. And at one time, I'm using 240 pieces, and once I'm only 70 pieces. So if we drop down and explode view, we can see that this guy has only so many pieces, and this guy has a lot more pieces. And then I'm switching based on a modulus function, which is based on the frame. So basically it says, it basically counts to 3, and at every 3, it switches between 1 and 0. So if I go 1, 2, 3, now it basically switched to this edge fracture, 1, 2, 3, and then it switched back, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So basically, every third frame, it basically switches between edge fracture 1 and edge fracture 2. And this is then used in the pointy form. And this is then used to, in this case, calculate velocities. Before, in the other setup, I said preserve original, so it created this kind of thing. Anyways, but you can see this is all the same as the fluid guy, and then this changed, and then this is the same again. And then let's go to the sim part again. We're importing what we just created. Now this attribute triangle now actually says something, and it says multiply my velocities by 10. So my incoming velocities that I have from the trail are just multiplied by 10. So we get like extreme velocities in the beginning. And then this gets created into a vellum object with the constraints. And then this switch actually does the same trick again. It says every 10th frame, you switch between nothing and this object. So, and here I do the same, but I say at every 10th, yeah, it's the same. So the only difference is that this vellum stitch node has multiple outputs. This one is the geometry itself that we're looking at. And then the second one is the constraints that it created. And those constraints are essential for a vellum solver because the geometry is just geometry with points. But the constraints are actually is the thing that tells the vellum solver if it's grains, if it's fluids, if it's a soft body, or if it's cloth. Or hair as well. So vellum is a multi-solver. So depending on how you create these constraints, it basically heavily influences the output of your simulation. So long story short, if I put this into a vellum solver, you can see that in the beginning, there is nothing. I'm just looking at the guides because I'm looking at the collision guides here. But in the beginning, up to frame 10, there is nothing, right? And this is because if you look here on the source, it switches every 10th frame to this. Otherwise, it's just displaying nothing. So this is why on the first 10 frames, the source is missing. So there is nothing in the simulation in the first place. And then for one frame, everything gets injected, the geometry and the constraints, right? And so it simulates on this one. And then 10 frames after 10, so frame 20, there is new geometry. And then frame 30 and 40, and you get it. And that's why this looks like this. The first 10 frames, there's nothing. Then this. Then the thing is, the cloth gets initialized, and then it kind of falls down and collides with the geometry. So I need new geometry that then to basically update the shape. Because if I would just emit this once and then everything falls off, then I wouldn't see the guy anymore, right? So I'm doing it basically every 10th frame, which basically means that every 10th frame I'm using the source again, and I'm using these heavily multiplied velocities that gives it this very explosive behavior that you can see here, and then basically slows down. So again, this is basically the output. And you can see the cloth, and every 10th frame, the velocities are quite crazy. But since cloth has a lot of drag, and I also increased the drag on the solver a tiny bit, it's very explosive, and then it kind of slows down as well. And I mean, I was doing a couple of things here as well. Like I just added pop wind actually. And the pop wind, the amplitude of the pop wind, so again, this ambient noise that you saw previously on the particles and also the fluid sims, the amplitude of that is multiplied by py, which means my pop wind has a big amplitude here. And the closer I get to py, so my y position, is to 0, it doesn't have any pop wind amplitude. So basically, once they reach the ground, they stand perfectly still. However, here at the top, there is a lot of wind, basically. So the higher it reaches, the more you can see they're actually wiggling around and stuff. And then the more they fall down, the calmer they get, basically, which is essential for the look of the thing, because as you can see, it kind of gives away the trick when you know it and you pay a lot of attention. But yeah, it's just one of the things that we do to make it more interesting. Cool. And then from here on out, it's quite similar. We don't have to create the surface out of particles, right? Because we already have the surface. So what I'm doing is I'm giving it fresh new velocities. They only change slightly, just in case there is some artifacts from the simulation. Then I'm creating an attribute called my length, which is basically based on the length of each velocity. And this is what I'm using in the shader later. So if I look at my length and display that. My length. There. You see it for one frame or so. Probably the viewport is frozen. This is what we discussed also at some point, that sometimes the viewport displays stuff that's not there anymore. So this is the attribute. And as you can see, if it's 0, it's purple. If it's 1, it's red. So if I remove all those in-betweens, it gets probably a bit clearer. Yeah. Come on. Like this. So the higher my velocity, the redder it is, basically, and the lower my velocity, the more purple it gets, basically. So that's why everything that is lying on the floor doesn't have any velocity. Everything that gets freshly born, like here on every 10th frame, is turning red because the initial velocity is quite high, right? That's why it's exploding. And also, generally, the velocity is higher at the top because of my pop wind. My pop wind adds this turbulence that is multiplied by the velocity. And that is the reason why this attribute looks like this. And I know we're running out of time, but just wanted to show you quickly the render setup. So again, I'm importing the cloth and the ground, merging in my camera, adding the dome light and the distant light, assigning materials, and rendering this through Karma XPU. And I mean, this is 98% the same tree, right? I didn't change anything here. The only thing that I changed is I changed the shader to read in the my length attribute, and that's what I'm driving the base color with this ramp, basically. And then just the source changed. Instead of the bubbles and the surface, I'm just importing the cloth. And the material assignment changed. And that's it. Everything else stays exactly the same as from the previous setup. And as you can see, it also renders pretty quickly and almost live. And the same is true for all the other setups. So no matter at what thing we look at, the source is different, the solver is different, and the shader assignment is different. Everything else is exactly the same. And that wraps it up for today.
Awesome. Thank you, Martin.
Confeti Guy. Sorry.
Sorry,
Go ahead. I was just thinking.
So how was the Confeti Guy different than the vellum or cloth guy?
Yeah. So as you can see, the Confeti Guy is not driven by velocities. So, it completely ignores if the velocities are high. So the shader doesn't have any change in that. The only difference was that it's much, much more pieces, as you can see. That's why they're also smaller. And basically I did I basically gave every resulting geometry, like every confetti piece, basically, a unique value with just the class attribute that we saw earlier. And this I was using to drive a random color on each of them, and that's it. So
cool. And the constraints are similar?
Yes, because it's both cloth constraints.
Yeah.
And so they're exactly the same. The only other vellum sim is this guy, the sand guy. And this has very different constraints, of course, because, not every point is connected multiple times to every other point. And the constraints are also much weaker to create sand instead of cloth, basically. Yeah.
Reminds me a little bit of N-cloth a very long time ago.
Yes, more or less. Actually,
this was all about N constraints and things like that.
Exactly. Also,
and you
like
could do all different materials. Yeah,
exactly. So yeah, I mean, I only have this week left, anyways. Next week I'm full on the Cinecide one. So I don't know. Like next time, I would potentially more talk about this guy, taking a simulation and then offsetting it in space based on curve and for each loops. Or we can go through, I don't know, the sand guy or whatever.
The pyro guy too. I mean, adding fire to it.
Yes. Yeah. I mean, I had this actually before. I wasn't super fond of it. That's why I killed it from my nuke session. But if you remember the very first time I showed the overview, basically there was also like a fire guy. But problem with fire is that it takes much longer. So it won't be as interactive as everything that we looked at so far.
I see. Originally, you scheduled just another appointment on this series, right?
Exactly, yeah.
Okay, let's see what you reckon we might squeeze in, and then it's going to be just enough.
Yeah. And again, if there's like, questions or like topics you guys are interested on, I'm happy to, create something new and talk about this next time.
Sure, that'd be great. So drop an appointment, like a meeting on as usual.
Yeah,
I'll be happy to join.
Cool.
But thank you very much, Martin. This is very, I mean, for my standpoint, my perspective, it's very interesting to see the potential. I don't have the ambition, frankly, to become an Houdini artist, but the process is very educational to me to understand even the pain of changing something or the opportunity on the other hand, on the opposite side, to change something in a say functional or effective fashion. So
Yeah.
Very nice.
I mean,
Appreciate it very much.
I'm also doing it, out of selfishness, because what I always want to, point out is that a lot of companies are switching completely to Houdini. They're also rendering in it, and there is a reason for it. And I think that reason is not very clear to people who don't understand, the concept of it. Because a lot, if you look at shows like Shang-Chi or anything like this, we were exporting terabytes per character to render it in Katana. And if you think about it, that's just
Doesn't make
super
sense.
insane. Yeah.
Yeah.
Just
I agree.
to have a couple of hairs of fur on him. And with Houdini, there's like hair procedural. You don't have to do anything. It just like sims and renders the hair on render time. And it comes for
I mean,
free.
I'm a big fan of efficiency, and this looks like a very straight line from what we actually doing in the practice of work to the immediate results. And this is the way to go. Absolutely.